Regulation of glycogen is really kind of very important, and the structure of glycogen allows us to degrade it very quickly, because sometimes we need a lot of sugar very quickly in terms of response to epinephrine. And so having both the synthesis and the degradative enzymes also allows us to take sugar when it's in the bloodstream very high and make it go very low back to normal, where we create the storage molecule very quickly. The speed is a biological theme, and having both enzymes means we have to have dual regulation. The same signal turns on one and turns off the other pathway. Pathways are normally regulated by hormones. And I taught this last semester. You should have seen this in cell biology in terms of signal transduction, where a hormone will hit a receptor on the outside of the cell. The receptor will upregulate a G protein, trimeric protein, that the alpha subunit usually is stimulatory, the beta and gamma subunit are regulatory, that separates. That alpha subunit picks up a GTP, it gives off a GDP and goes to an enzyme called adenylate cyclase, which creates cyclic AMP. That cyclic AMP then goes and upregulates protein kinases. The most studied that we look at is protein kinase A. And that kinase is going to phosphorylate specific enzymes. And in the last chapter that I taught that pathway, we said cellular response. But we didn't tell you what the cellular response was in a lot of cases. Here, we're going to show you acellular response. So we get a signal, kinases are active, I'm going to phosphorylate. Or we get a signal, and in reverse, we're going to have a protein phosphatase active. And so we're going to phosphorylate or dephosphorylate and turn on and off certain enzymes. And so if by chance you have defects in glycogen enzymes, it can be fatal in some cases. Glycogen degradation is done mainly, but not exclusively, but the most reaction occurs from glycogen phosphorylase. From this point on, we'll probably refer to it just as phosphorylase. It uses an inorganic phosphate, which is kind of really great, because you have just a linear chain of sugars that is branched, and if you react it with inorganic phosphate, the outcome is a phosphorylated glucose. Remember, when we first got glucose into the cell through the transporter, we had to use ATP and hexokinase to put a phosphate on it. It used energy. Here, I'm going to use inorganic phosphate and add it on, and I will phosphorylate a sugar and have potential energy without the use of ATP. There is a mutase that will make it from the glucose 1-phosphate to the glucose 6. That is actually in equilibrium, and so that works in concert with the degradation to get it into the form that we need. So phosphorylase will break the alpha 1,4 linkages. Doesn't require ATP to have a phosphorylated intermediate. It is also charged, so it doesn't bind to the transporter. It stays inside the cell for use. Usually, at this case, the degradation through glycolysis. And so phosphorylase will work on all of the glycidic bonds on all of the ends of all of the glycogens. So it can release a lot of glycogen very, very quickly. But as it gets closer to the alpha 1 branch point, phosphorylase can't fit the substrate into its active site. It has to have a long chain. So at this point, phosphorylase cannot work. All right, and it is a steric hindrance. All right, it just doesn't fit. So we need another enzyme, all right, called the debranching enzyme. The debranching enzyme has two activities. One is a transferase. It will shift 3 residues from the alpha 1,6 branch point and stick it onto the other length of sugars. Phosphorylase could bind to that and start degrading, but the transferase is not done. What the transferase has a second activity, which is the debranching or alpha-1,6 glucosidase activity, and it lets go of glucose. Now here is the important part. This glucose goes out as glucose, and every other one is released as a phosphorylated intermediate. So that glucose needs to be rephosphorylated, and that means we have to invest energy to get it back into the form to get into glycolysis. All others released don't. The enzyme then can degrade until we reach another branch point. In terms of what we see, okay, if I looked at the reaction over time, okay, so if I look at time and you look at glucose 1-phosphate release, okay, what we see is a very quick rate of glucose being generated. And then we see for the rest of the reaction a much slower production of glucose over time. This is called a burst phase. Sometimes we see this in biological systems in which you get a lot of product and then all of a sudden it isn't this simple curve to another rate. You go to another rate at a very sharp or distinct place. This only occurs when you have reactions in stepwise mechanisms or multiple steps mechanisms. If by chance you're running a relay, you can only go as fast as the which step? The slowest step. And so phosphorylase is a very fast enzyme. And phosphorylase has a lot of substrate for all of those ends, and so a lot of glucose can be produced very, very quickly. The debranching enzyme is much slower. After I've degraded all of the ends, then I run up against the debranch point. The debranch point, the branching enzyme then overwhelms or slows down the overall rate, and the reaction cannot go any faster than the debranching. And so we give a lot of sugar all of a sudden, and this is great when epinephrine is released. The fact that it changes its rate is also great. Why would being able to change the rate to a slower pace be very good for your survival? That's exactly it. If by chance you just had long chains, phosphorylase may give off all of your energy stores in a very short time, overwhelm the system, and then you use it all up. And so in this case, you get a very large burst in which you could sprint away from the lion, but then release glucose at a much slower rate so that you can continue to run at a slower rate but for a very long time to get away. And so it allows us, and this structural organization allows differential timing in which we use the glucose for a very quick, intense amount, and then over time we allow just a slow release of glucose. Not as quick in terms of getting to the energy, but allows us to utilize it for a much longer period of time because there is just a limited amount of glucose in your system. All right. Now, most of the glycogen is used in different ways. The largest amount of glycogen is stored in your muscle. It's because it's lower in concentration, but you have more muscle mass. Any glycogen that is released from the muscle into glucose is normally used for glycolysis, creation of ATP. The tissue that has the greatest concentration of glycogen is in your liver. The liver, when it releases glucose, almost exclusively releases it to keep blood level concentrations constant so that you have enough binding to the red blood cells in the brain. And so depending upon where you are, that glycogen is used for two different reasons. And so here, phosphorylase is much faster. That's why we have the bursting. And then the slow point comes because of the debranching. Now, the glucose 1-phosphate produced converts into glucose 6-phosphate by a mutase enzyme. And we had a mutase enzyme in glycolysis where we shifted it from 3 and 2. And the intermediate inside the enzyme was a phosphorylated intermediate that had both of them. We also have that strategy here. And so the mechanism is so messed up in this particular reaction that I'm appalled, actually. Deprotonate, then that attacks, remember, kick up, kick down. All right, so that one just missed some. All right, the serine comes in as phosphorylated. Now this one just, it just really, really messes me up, okay? You have to deprotonate the proton, and the electron pair attacks at the phosphate. Electrons up, electrons down, and that picks up a proton. That one just, they get a failing grade on that step. And so the phosphate is exchanged. I have glucose 6-phosphate. Why the serine reacts with the 6 initially and why it reacts with the 1 in the second step is the phosphorylated intermediate binds the sugar such that the 6 is right next to that serine. When it lets go of its phosphate, the enzyme has a conformational shift. It actually moves and places the serine closer to the 1. And so by becoming phosphorylated or desphosphorylated, the protein shifts its shape, not very well seen in a two-dimensional structure on a slide, but that's why we do that movement. Same reasoning we saw in glycolysis. If I take a look at the mechanism of phosphorylase, again, I don't want you to draw the arrows, but I want you to understand what happens. We have, at the beginning, an alpha conformation of the oxygen connected to the next sugar. We will produce a glucose 1-phosphate. There's the oxygen, okay? And a phosphate will be also in the alpha conformation. And so the sugar is in an alpha and the phosphate is in alpha. Now, one way that you might think this attack might be would be the PI comes in, it's got a lone pair. If it attacks there and that falls off, I just displace the long chain of the sugar and now I have a phosphate. The problem is that kind of mechanism would have an inversion. I would have beta phosphate, not an alpha. And so that can't occur, and it's similar to what we saw in lysozyme, that if you retain stereochemistry, then what we're going to have to do is have a carbocation as its intermediate. The phosphorylase has a organic cofactor called PLP. It's a vitamin B derivative. And so this is sitting inside the active site. That will help mediate the reaction. If you actually take a crystal structure, we do know that phosphorylase is a dimer. There are 2 catalytic sites. And if you take a look at the catalytic sites, this is what we've got going on. We have the lysine that has the cofactor. The important part of the cofactor is the phosphate that it carries. Okay, that's going to coordinate. Then we have a lysine, an arginine. Lysine and arginine have what charge? Positive. And remember, we're reacting with inorganic phosphate. And inorganic phosphate has a lot of negatives. So these positives and this phosphate that has a proton orients the phosphate, the inorganic phosphate, so that it can do its attack. Okay? So this is what happens. Here's the enzyme, there's the lysine, this is the phosphate of the cofactor, that's its proton. Here's the incoming phosphate that's going to do the reaction. We have arginine, we have lysine over here that are balancing out this charge. We have the long chain, the alpha 1,4 of the glycogen. And what happens is, this long chain, the oxygen that makes the O-glycidic bond, hydrogen bonds to a proton. For it to leave, it needs to pick up that proton. And so what happens is, the electron pair will come and pick up the proton. Now what will happen most likely is this bond pair will pick this up, and these pair of electrons will take what that bonding pair was doing on the oxygen. This pair of electrons then kicks in, and then this pair of electrons takes this proton off of the PLP to stabilize its reaction. So this phosphate has to have one hydrogen. It will donate the one that it brings in to the chain that is leaving, and it will take the proton away from the PLP to have a 2 charge overall. I've created the long chain that falls off. Here's the single sugar unit in a carbocation form. And now the carbocation sitting here, now this oxygen is not a hydroxide containing, it's negatively charged, which then can attack from below, creating the right stereochemistry. And so, knowing that the stereochemistry is retained in the substitution, we have to go through a carbocation intermediate, which is an SN1 attack versus an SN2. All right. Its main regulatory event is hormonal. And so phosphorylase can be in the active form or the relaxed state. We also call them phosphorylase A active or B inactive. Where does the term relaxed state and the tense state come from? Do you remember? It was associated with one protein that we learned, and I told you we're going to use that as a generalization from that point on. To one of the first proteins that were identified and studied and we had a crystal structure of, and it had allosteric interactions when it bound to something.
Is this one that release feels like that alpha beta release the ATP? Or one that like the circular cyclic ATP?
They both do that, but the first one that we talked about was hemoglobin. Hemoglobin was in a tense form when it didn't bind oxygen and was in a relaxed form when it did bind oxygen. And it really came down to there were more ionic bonds in a tense form that made the structure rigid. And in the oxygenated form, it actually had a lot more movement. And so there was a real tense and a real relaxed in that particular protein. Now when we apply it to any other enzyme, tense means it binds substrate less, relaxed means it binds substrate more. It has nothing to do anymore with if it's more tense, or relaxed. It just indicates whether I'm going to bind to or I'm not going to bind to the substrate. So in this case, what happens for phosphorylase, and this would be kind of the thing that you really kind of need to know, insulin will upregulate a phosphatase. Okay, so it dephosphorylates things. And so in this case, the phosphorylase phosphatase will take off all the phosphates. So insulin says, I've got a lot of sugar. It takes off phosphates off of phosphorylase to create an inactive form, because if I have a lot of sugar, don't break down my sugar stores. Okay, I already have glucose. And that is an indication I don't need to produce from my stores any more free glucose. On the other hand, glucagon, which is a low-fed state, will be sent out when there's not a lot of sugar in the bloodstream. And so if your cell does need some glucose, the glucagon will upregulate a kinase, it'll phosphorylate it, when it's in the phosphorylated state, it is going to release glucose from your stores to service in the muscle that particular for glycolysis. Really in the liver, it's going to allow glucose to be released in the bloodstream. All right. Epinephrine, doesn't matter if you're well-fed or if you're in starvation state, you need glucose. And so the epinephrine will override everything, phosphorylate the phosphorylase, which will create lots and lots of glucoses. And so we have hormonal response, which usually is a covalent modification, quite frankly, almost always either a phosphorylated or dephosphorylated state. There is also an allosteric mechanism that can shift these things. And so in epinephrine's case, we said that I get phosphorylated and I am active. That's great. And we said that in insulin's case that this is a signal I have a lot of sugar around, make it less active. Okay? Now, there is a chance that the cellular conditions inside the cell is not the same as the bloodstream. Okay? If it is actually the same as the bloodstream, what you're going to see is you have glucose 6-phosphate, or ATP, roaming around when you have a well-fed state. If you are bringing in lots of glucose, it's getting phosphorylated, and you have lots of ATP, there's a binding site that's regulatory that either one can get into, and it will even further lower the activity. So the phosphorylation state says stop. If you bind up here with any one of those two, it says stop even further. Now remember, enzymatic activities are raised and lowered, not turned 100% on and 100% off. Okay? So for it to be very low, it has to have the hormonal dephosphorylated state, and it has to have the molecules bind.
Just to clarify.
Yep.
The inactive state means
It's not breaking down glycogen. It's not breaking down glycogen. Now, here's the deal. You could have it in the dephosphorylated form. So insulin is around, but inside that particular cell, especially in muscle, you could have high AMP concentrations. High AMP indicates that you need ATP synthesized. If you're in this state that the hormonal signal says stop, but you have an indicator, an allosteric indicator saying that you really need to go, it can bind in that regulatory binding pocket and make phosphorylase work at a small level. Okay? So this would be at maybe 20 or 30%, right? Because I have two conflicting signals. The rest of the body might be fine, but this particular cell needs some glucose, so it'll release a little bit. Okay? This indicator here would be very close to zero because both of the signals say stop. This right here will be very fast because the hormonal response says go. And so we can have a balance or mix signals to get a modified level, not necessarily just 100% and 0%. In liver, it's just a little bit different in terms of its regulation. The signals for glucagon and epinephrine, again, will make it go very, very quickly. All right, here, the dephosphorylation is in the tense state. Okay. There is a state that if you are turned on by the hormonal response, but if you have lots of glucose in there, it can downregulate it so that this says turn on, that says turn off, so it's working just a little bit. Okay? The only time you get totally turned off is the absence of glucose and the hormonal response. And so liver cells are just a little bit different in their particular response to the signals. All right, glycogen synthesis is not the reverse Okay, we never have that, but they are all happening right at the same spot. In this case, we need a activated unit that is the reactive species that will take the glucose and make sure that it grows. We're going to use the energy from UTP. Unique, we don't use UTP a lot. Usually we're using ATP, and then most often after that we use GTP. UTP is used in a few areas. Here's one case. Now, what the activated unit will react with is glucose 1-phosphate. And so if you eat your Snickers bar, it's in glucose in the bloodstream. When you get it through the transporter, it gets phosphorylated as glucose 6-phosphate in the bloodstream. And then the mutase has to create it to glucose 1-phosphate for it to go to glycogen synthesis. And then I have to activate it by reacting it with UTP. I will get a UDP glucose. This is the original phosphate from the glucose 1-phosphate, and this phosphate comes from the UTP, and we lose 2PI from the UTP as part of this reaction. And so the phosphate will attack at the alpha phosphate of UTP. The diphosphate falls off. Now, what's important about the diphosphate coming off is we break those two down into two inorganic phosphate. That actually also provides energy. So this is actually very costly. It actually uses 2 equivalents of phosphate to do this reaction. And so what the leaving group will be is this activated species. Then glucose will be added to the growing chain. The reaction, again, we saw now 2 slides. Glucose 1-phosphate reacts with the UTP to make the glucose added to the diphosphate. Here's the growing chain. This will react with this sugar, and the UDP will be the leaving group. Looking at the stereochemistry, this is below the ring. The addition is below the ring, so we're going to have to go through a carbocation intermediate. I can't attack at the top and it fall off at the bottom. And this will grow the chain in the alpha 1,4, which is the majority of what glycogen is. But it isn't a straight chain. Okay? We actually have to do branching, so we have to have another enzyme. One other thing about glycogen synthesis. Glycogen synthesis just doesn't happen on its own. In the center of every glycogen is a protein called glycogenin. Glycogenin has a glucose that is covalently attached to it, and glycogenin has its own activity that can add glucose to it. So it autocatalyzes, and it'll add about 8 glucose units to itself. This creates the initial place where I can grow glycogen from. And so the enzyme glycogen synthase will bind to glycogenin and add on to that growing sugar chain. What's interesting about the glycogen synthase is that glycogenin and glycogen synthase, when they bind, the glycogen synthase becomes more active. This also allows the glycogen to be synthesized very quickly when it's close, but it slows down when it's not bound to the glycogenin. This limits the size of how big it can get. Okay? So we keep it all compact and we start branching it out. And so it doesn't get these long, long chains. We get little bundles or granules, and that's what you see in the cell. Glycogen synthase will make all of the alpha 1,4 linkages. The branching enzyme makes the alpha 1,6. And so we had phosphorylase and a debranching enzyme to break it down. We have glycogen synthase and the branching enzyme to synthesize it. The branching makes the glycogen more soluble, and then the speed at which we can degrade it becomes greater. The branching enzyme has a lot of specificity. Okay? The branching enzyme can only work if the length of the polymer is at least 11 residues, it must transfer at least a block of 7 residues, and it has to transfer it at least 4 residues from any branch point. When it all comes out, on average, the branching points come out to an average of 10. It is not every 10, it's an average of every 10. And so you can find branch points that are as close as 4, but you may then have a much longer branch point that is down the ways. And so you have to have a long enough piece, it has to transfer only 7, and it must be 4 away. The overall reaction for its synthesis, we take the glucose, convert it into the 1 form, UDP to create it into the activated form. The pyrophosphate gets broken down. The glycogen that is growing will react with that activated glucose. UDP is released, and then it has to be rephosphorylated up to the UTP to be regenerated. Overall reaction is really looks simple, but there are multiple steps. If you think about its efficiency, okay, when you put it into the synthetic process, you actually take off the phosphate and you put it in a polymer just with sugar. But about 90% of it converts back into a phosphorylated intermediate. So you can recover about 31 ATPs from the total degradation of glucose in the largest amount of glucose, ATPs that you can make. Only 10% that branch point comes off as glucose, which you have to use an additional ATP to get it to a phosphorylated. So you get 30 ATPs as possible of the 32. By storing glucose in the form of glycogen, we can recover 97% of the energy. That is much better than any other way that we try to store energy ourselves, in a battery or any other form. This is highly conserved in terms of energy. Glycogen synthase regulation occurs again mainly with signals. And so in this case, if we are going to have glycogen synthesis active, then what we do is we have to phosphorylate it. And so all the signals for glycogen synthase to be active, sorry, I said that backwards. For the glycogen synthase to be inactive, we've got to phosphorylate it. So glucagon and epinephrine will take and signal stop synthesizing, because I either have not a lot of sugar around, or in epinephrine's case says, I'd rather degrade it for energy rather than store it at this moment in time. And then insulin, when I have lots and lots of sugar, I need to have the synthase running so I can store as much as I can possibly, and that will cause that is done by the phosphatase taking off the phosphates. And so the main regulation is phosphorylation or dephosphorylation. Unfortunately, there are a lot of signals that happen for the phosphorylating event, and so you've got protein kinase A working on it, protein kinase C, glycogen synthase kinase 3. There's a lot of different places that the glycogen synthase can be phosphorylated. And then under epinephrine, there's a whole other phosphorylated state. There's not just 2 phosphates. This thing can be phosphorylated multiple times in a lot of different places. And each phosphorylated state will notch it up a little bit. It is very hard to get glycogen synthase 100% active because you need multiple phosphorylations to occur for that to actually get up to fully phosphorylated state. It's a little bit more simple. The protein phosphatase 1 takes off all the phosphates, and so transitioning it back to its active state is much more simple to do. The glucagon and the insulin, only given off in two very different states of glucose levels in the blood. They are both bound by a particular receptor. Glucagon upregulates phosphorylation. The insulin induces dephosphorylation. And so what happens in this case is that if I phosphorylate everything in terms of glycogen, I get the synthase here, the synthase, all right, in the inactive form. And I get the phosphorylase in the active form. Low glucose blood sugar levels and glucagon stops synthesis and starts degradation by phosphorylating all the proteins in the granule. And then we have glucose that is released. All right? In that case, the glucose has the possibility to be broken down by glycolysis or to be exported. It is broken down a lot of times in glycolysis if you're in the muscle, exported if you're in the liver. Okay? The insulin release goes through and upregulates a phosphatase that will take off phosphates on every enzyme in the granule, leading to the degradative enzyme being downregulated and the synthetic enzyme being upregulated. I will synthesize glycogen, and the glucose transporter will be working in the import of glucose so that I have the substrate to actually synthesize glycogen. And so we can have dual regulation, whereas I upregulate a kinase and turn one on and off, or I can do the phosphatase, turn one on and off. Now, why in the world could you get, we talked about the hormonal response is one direction, but we have steric or allosteric interactors. Here's an example. High blood glucose. You eat a Snickers bar. I make sure glycogen is upregulated. Glucose is being brought in. Glucose being brought in. All right? I eat a second Snickers bar or a third Snickers bar because I just want to. Okay? You may have a hormonal response that says synthesize glycogen, but you may have completely filled that level of glycogen at its maximum. And so even though you have a hormonal response that says create glycogen, there's a chance that you could overwhelm the system. Glucose will still come in, okay? And so what will happen is the allosteric effector can overwhelm the cell to start making it break down into smaller bits, but I might not, let's say, send it into the citric acid cycle. I might make lots of acetyl-CoAs, but I don't need energy because I have lots of glycogen, I have lots of citric acid cycle intermediates and lots of ATP, but I still ate too much Snickers. So what will happen is that sugar in the acetyl-CoA is a substrate for fat synthesis. And so I could be hormonally wanting to make glycogen, but the allosteric, what actually happens in the cell could send it down a different pathway. And that's why we have both a hormonal response and an allosteric response inside the cell. Another look at this in terms of a glycogen breakdown or synthesis, we also have response of glycolysis or gluconeogenesis. And so those same responses where we just looked at the two here and the two there also will either upregulate or downregulate glycolysis and gluconeogenesis. Those same signals are moving and controlling those particular pieces of the puzzle. They do control it almost exclusively through the concentration of the fructose 2,6 bisphosphate, whether it's there or it's not. And that's the main control point.